Beyond the Milky Way. Today, any kid with an interest in Star Trek knows that we on Earth live in the Milky Way galaxy, one of many galaxies in our universe. But in the early 1900s, this theory was quite foreign. In 1924, an American astronomer named Edwin Hubble peered beyond our galaxy and enlightened humanity to the true expanse of the universe we live in. He saw billions of other galaxies, and he saw that they were moving, constantly expanding, and separating from each other. These revolutionary discoveries now cover most of what astronomers study. The expanse beyond our galaxy is infinitely larger than what we have here. Unfortunately, we are limited in our study to what we can observe, and with even the largest telescopes on Earth, we can manage just glimpses of what lies beyond the Milky Way. The main issue that astronomers faced is that light becomes distorted as it passes through the Earth's atmosphere. As it comes in and passes through layers of the atmosphere at different temperatures, the waves become distorted as a result of turbulent mixing. Light becomes refracted in many different ways. The most common interaction we have with this phenomenon is the twinkle of stars. Just a year before Hubble made his discoveries, in 1923, one of the fathers of rocketry, German scientist Hermann Oberth, theorized how a telescope could be propelled into Earth by a rocket. 20 years later, an astrophysicist at Princeton, Lyman Spitzer, formulated a paper detailing the scientific benefits of a telescope in space, and with that, the process of developing orbital astronomy formally began. One of NASA's first projects was the Orbital Astronomical Observatories program, the first iteration of a space observatory. This program launched 4 satellites between 1966 and 1972. 2 of the launches failed, but despite that, the program was overall a success, and it generated further interest in the seemingly endless potential of orbital astronomy. During this time, NASA began researching the possibility of a large, multifunction space telescope. In 1969, the National Academy of Sciences gave approval for the Large Space Telescope project, or LST. With that approval, NASA began the research and development of what we know now as the Hubble Space Telescope. The Large Space Telescope was to be part of a series of 4 space observatories, known as NASA's Great Observatories. Each one would record data from a different part of the electromagnetic spectrum. The Large Space Telescope project moved forward, gaining steam and international appeal. In 1975, the European Space Agency, ESA, joined the project, contributing financially and mentally. In 1979, they got the final go-ahead, congressional approval. Development began, and the numerous tasks were divided up among dozens of contractors, universities, and NASA centers from 21 states and 12 countries. The design of the instruments was severely limited by the total weight allowance for the observatory, and by financial restraints made by Congress. The LST Science Working Group therefore decided that the telescope would be launched with 5 instruments, but designed so that each one could be exchanged or upgraded. The lead scientists expanded this philosophy to the entire telescope, and this ability to be upgraded, and therefore repaired, has saved the telescope on numerous occasions. Fully constructed, the Space Telescope was 43.5 feet long, 14 feet in diameter, and weighed more than 24,000 pounds, about the size of a school bus. 2 solar panels powered the computers which record and transmit data. For the 27 minutes when the telescope passes through the Earth's shadow, the telescope uses energy stored in nickel-hydrogen batteries. The instruments currently equipped with the telescope are the Cosmic Origin Spectrograph, which is one of 3 spectrographs on board. Spectrographs do not record images, but instead separate the different components of the light to find the temperature, density, chemical composition, and velocity of the object emitting the light. The Wide Field Camera, which has captured the majority of the images that have made the telescope so famous. And the Near-Infrared Camera and Multiple Object Spectrometer, the Advanced Camera for Surveys, and the Space Telescope Imaging Spectrograph. Lastly, the Fine Guidance Sensors, optical sensors which maintain the direction of the telescope. There are 3 on-board working in conjunction. They allow a maximum deviation about 7/1000ths of an arc-second, or about the width of a human hair seen at a distance of 1 mile. But besides for some fancy instruments and its position in space, what makes this space telescope so spectacular? How does it work? The answer is the mirror sequence, which directs and concentrates the incoming light for reception by the instruments. The sequence involves 2 mirrors. The primary mirror was one of the largest mirrors ever crafted. Overall construction and assembly took nearly a decade. After the blank was constructed, it was sent to be grinded and polished by expert opticians. Laser guidance systems guided the polishing to a precision of 1/800,000th of an inch. That mirror, the primary, has a 24-inch hole at its center, above which the secondary mirror sits. When incoming light waves hit the primary mirror, they are reflected onto the secondary mirror and from there, through the hole in the primary mirror to the focal point from which the instruments gather data. With the last piece in place, NASA began preparations for launch. The telescope was to be flown in one of the newest parts of the space program, the Space Shuttle. Now officially ready, NASA gave the telescope its official name, the Hubble Space Telescope, to commemorate the man whose discoveries 7 decades earlier led them to this momentous and historic occasion. The telescope was scheduled to be launched on the Space Shuttle Challenger, but when the Challenger disintegrated, this halted the Space Shuttle program and the Hubble was grounded. 4 years later, NASA announced on April 24, 1990, aboard the Space Shuttle Discovery, Hubble would get its chance. From Cape Canaveral, the launch went smoothly, and the Hubble Space Telescope was finally deployed. It achieved orbit at 380 miles above the Earth, inclined at 28.5 degrees to the equator. Moving at 17,500 miles per hour, each orbit takes 97 minutes. A few days later, when Hubble began transmitting images, they noticed a problem. The images were fuzzy and imprecise. The main error they soon discovered was caused by a malfunction of a measuring device used during polishing. The problem is called a spherical aberration. They found that the edges of the mirrors were 4 microns too flat. That difference, 1/50th the thickness of a piece of paper, caused distortion and inhibited most of the telescope's capabilities. Engineers worked diligently to solve the problem. They crafted COSTAR, the Corrective Optics Space Telescope Axial Replacement, which is essentially a giant contact lens to fix the spherical aberration. In December 1993, astronauts departed on the first servicing mission, their most important task, installing COSTAR. This was the first of 5 service missions which have enabled Hubble to operate well beyond its original 15-year assignment. The installation was successful, and scientists could now clearly observe parts of the universe light years away. From Spitzer's idea in 1946 to its launch in 1990, no one could have predicted the success that the Hubble Space Telescope would have. It is the most productive scientific tool in human history, transmitting over 120 gigabytes of scientific data every week. In 2011, it made its 1 millionth observation, having led to 10,000 published papers. In April 2015, Hubble had its 25th anniversary, and today it is still one of the foremost tools we have to understand the cosmos, the universe, and what lies beyond the Milky Way.